Hello everyone, myself Harsh Gorade. Today we will be discussing about shell balance application in momentum transfer. And in that we will be discussing about flow through circular and cylindrical annular region. Cylindrical annular region. In this problem, we will be dealing with steady laminar flow and incompressible Newtonian fluid. So these are our current assumptions. We have already studied that cylindrical flow, it's pretty similar to that only, but we are just doing it in annular region. So in this case, our very first assumption will be steady laminar flow and incompressible Newtonian fluid. So the variation of density and viscosity are not there. So d rho by dt, or we can say it's zero. So let's move further. And so our main objective here is to get the velocity profile only by governing the differential equation. We'll see. We will reach to the velocity profile because consider the assumptions I told you earlier that they're that only. So we will use shell momentum balance. Okay. So what is annular region? The annular region is the region between two concentric cylindrical. So like this is the first cylinder and this is the second cylinder. Like this is the first and this is the second cylinder. This region is the annular region. So this annular region we will be talking about, and so this region we will be talking about. Hmm. So our assumption are steady and incompressible flow, axisymmetric flow, fully developed flow. So in this the velocity components. Let's talk about the velocity components. The velocity is the water or the liquid in the cylindrical annular region is flowing in upward direction, in this direction. So there won't be any velocity in Vr and V theta. So we will have only left with only one component Vz. And as we know, Vz can also be function of R, theta, and Z. So since the flow is fully developed, there won't be any end effects. So dou Vz by dou Z will be zero, and so the it won't be the function of the Vz won't be the function of Z. It won't be varying in Z directions. And when we talk about theta, it's the symmetric. It will be symmetric about the theta. That means all the forces acting on that particle in theta direction will be cancelling out each other. So it will be zero. So Vz will vary in only radiant direction. This will be zero because there is no flow in that direction. And when it comes to Vz, it will be only R direction. The two reasons. One is that no end effects, and another is the symmetric. Uh, so there is no velocity in r and theta direction, so there won't be any momentum. Momentum will be in z direction only. So momentum will be have three terms: v phi rz, phi theta z, and phi zz. As it's a tensor quantity, there will be nine terms, but as no momentum is there in theta and r direction, it will be zero. So we'll left it only three components. So phi theta z. Let's talk about angular flux term. So as we know, the generalized formula del ij will be zero. So there won't be any pressure term P del ij. So it will be cancelled out. V theta is zero. So the first term, this first term will be zero. And as dou Vz by dou Vz by dou theta will be zero because symmetric about it. So it will be zero. So V theta will be phi. This whole term will be zero. So this will be zero. We will remain it only phi rz and phi zz. These are the only two flux component we have. First we cancel out six components as no velocity is there, and phi theta z cancelled out because these two conditions. So we left it only these two components. So let's go more. So now let us assume a cylindrical shell of radius r, thickness delta r, and length l. So I will show you how the cylindrical shell will look like, somewhat like this. Uh, so this is r. So it will be going from R to delta R, like for very thin part, everything will be same. So this will be the differential shell. This part, this is the shell part. So it will go from R to delta R. This small thickness is delta R here. So this is how our shell will look like, differential shell. It will be so it will be, we will be considering this to integrate further. Uh, so as we know, their area will be varying as we will be moving with R to delta R. The area will change. So we will be talking about, we will be considered, we won't directly take flux, we will be take rate. So while taking rate, we need to consider the area because flux into area will be the rate. So in flux we take perpendicular area because it's a cross product. So we took for perpendicular area in flux for flux. As phi z is there, that means in z direction, the area perpendicular to z, area perpendicular to z will be this area, this bottom area we can say. Wait, this area, this circular area, this circular area, because z direction the momentum will be in this direction like this, so the area perpendicular will become this only. So it's like a circular area, you can see, where the area will be 2 pi r and some area to make it a shell delta r. So 2 pi r delta r, this will be the area, 2 pi r delta r for r if z equals to 0, and same area will be at z equals to L. So these are the two terms, one is entering and one is going out. So it's a shell actually. We will be integrating from 0 to L, and this is how it will be looking like. So this is the first case for phi zz. Now we will be going in radial direction. So when we will go in radial direction, like in this direction, this will be the perpendicular area. This will be the perpendicular area. So as we can see, the perpendicular area will be somewhat 2 pi r into L, because this is the whole L length and 2 pi r will be the circumference. So this total area will become 2 pi RL. That will be the perpendicular area of that thing. So 2 pi RL. So these are the two going in R 2 pi RL into phi RZ, and radial for output will be 2 pi R plus delta R into L phi RZ. So these four terms we have, and then gravity. So gravitational force will be acting downwards. So it's nothing but V rho g only, mass into gravity. It's only this is the volume and this is the density. So it will be mass mg. So that's mg only. This will be the complete balance equation, inward, outward, everything balanced. So after dividing by 2 pi delta RL, we have done nothing, just divide the whole term by 2 pi RL, 2 pi delta RL, and take R phi RZ term one side and phi ZZ term another side. So we will get something like R phi RZ minus R phi RZ at R plus delta R divided by delta R, and delta R will be tending to 0. So it's for very small units. So it will become differential of R phi RZ. So we have differential of it del dr phi r d phi rz by dr, and these are the remaining. It just rearranged and divided by 2 pi delta r into L. So now let's talk about the uh, flux. So phi rz and phi zz were the two terms remaining. As we know, their generalized Newton formula. So we can say that tau rz plus vz will be remaining, and the p del ij, that pressure term will be 0 as del ij will be 0. So and Vr is 0. So phi rz phi rz will be only tau rz, because this is 0 as Vr is 0, and we will remain with only this part. In phi zz, pressure term will be there. Tau zz will be 0 because dou vz by dou z is 0. This variation is 0. So it will be 0. And interesting part is this rho vz square. So rho vz is there. Vz is there. But rho vz square is still there. But why it's not in this term? The reason is, in this formula, as you can see, phi zz minus phi zz at 0 and L, we are taking the subtraction, so it will be same only. There won't be any change. So the total terms rho v square minus rho v square only, that will cancel out, and we will remain with only pressure, only this part, only this part, only this part will be remaining about. Like it's not this, it's plus rho vz square, but in while substituting it will become 0. So we will be considering this. Now the pressure term is there and rho g r is there. We combine both the terms p and rho g r. We combine both the terms and call as total pressure p naught minus pl by l. So this is what we will getting. We will be getting. This is what we got. This is the differential equation. Integrate it. Take dr this side and integrate. So we'll get this r tau rz. Divide this equation by r. So after dividing, we will get this. This is tau r. So we obtain tau rz. Now, as we know, tau rz will be minus mu dvr by dr. We saw that tau rz term is not 0. So substitute this minus mu dvr by dr. We already have one. We already remain with one constant. Integrate it again. It's pretty simple integration. Just divide mu, take dr that side, and integrate. So what we did, we had the differential equation. First we integrated, we got tau rz. Then again we substituted, we integrated, we will be getting vz. So this is the final expression we'll be getting. Now here we have two unknowns, sorry, two constants. So for these two constants, we will be require at least two boundary conditions. And as we can see here in this figure, at this surface and at this surface, there will be no slip boundary condition. So due to no slip boundary condition, the velocity here will be zero. So the velocity will be zero here for R and KR at both the terms. So Vz will be zero there. After just put zero here and equate both the equation. C2 will be cancelled. We will directly get C1. So we will get C1 directly. Just subtract both the equation after putting boundary condition. Put this C1 in any of the boundary conditions in this equation. We will be getting C2. So this will be after substituting C2 and C1, we will be getting this final expression of velocity. So that's what we were looking for. So this is our what we can say. This is our velocity profile for cylindrical annular region. You can look at the formula carefully. Yes, so the velocity profile will be this here no slip boundary condition, so velocity will be zero. There will be zero. In between somewhat k r and r, there will be it will maximum at certain point. So it will be lambda r. So this will be our velocity profile, something like this from both the sides. And corresponding flux profile will be it will be zero where the velocity is maximum and something like this. So we'll be getting both the profile even without directly using the equation biologically. So yes, we got our velocity profile. That was our objective. Now let's see some problems here. So the conclusion here is by applying shell momentum balance, the velocity different distribution we got as a function of radius. So we can calculate Vmax or average velocity, everything accordingly. And for average velocity, we can directly integrate AVZ into dV divided by area. We will get average velocity. It's very simple. And for VZ, just differentiate it once and equal to zero, we'll get maximum velocity. So yes, the derivation is complete about the cylindrical annular region. Let's move towards some problems. So yes, this is the first problem. Flow of film on the outside of a circular tube. So there is circular tube means a cylindrical cylinder only. Circular tube is just vertically it will be cylinder only. So there is a viscous liquid flows downward as a thin film over outside of a vertical cylindrical tube. The flow is steady, laminar, and fully developed using shell momentum balance and Newton's law of viscosity. The velocity distribution of mass flow rate. So we have to find the mass flow rate and velocity profile only. That's the same as we did earlier. There is a tube. Okay. So we have to show velocity distribution. We have to expression for mass rate of flow and simplify it for very small thickness. Like the if the water is moving from above the circular tube, if the thickness will be very small, means very small water is moving, then what will be the formula? We will see everything. So let's move ahead. So this is the problem only. Like this is the water moving above the cylinder, above the circular tube. That means cylinder only. So they are already given the velocity distribution inside. It's same only. It's the same. So they are already given it. We have to solve this problem. So we will be taking the same approach only. Here also there won't be any velocity in VR and V theta direction. Flow is going only downward direction. So same. Everything will be same. Will be the same. So now again taking a very small again taking a element cylindrical shell of thickness dr, radius r, length l, and this is the expression we will be getting. Why I written this directly? Because we have already done this. What was in that problem? In that problem we had P naught minus PL by L plus rho gr. But here no pressure term is there. So we will be directly getting rho gr is equals to d by dr into r tau z. Uh, because it's as same as that of cylindrical annular region, because in that question there were two cylindrical tubes, concentric, and liquid was flowing above first one and between the second one. In this case what's happening? The same only, but there is no second cylinder is there. Like it is forming a film over the first surface. So the end part of the first surface will be of the liquid only, not of any cylinder or anything. So the reason of not pressure term is there, it's exposed to environment. So P naught minus P naught will be zero only. So we will be taking only rho gr. As you can see, I'll be showing you the previous slide. Mm, yes. So it is the same. It is the same. But here only the rho gr term like this was here. We'll be taking this only. as pressure is 0. Pressure difference is 0. Pressure not 0, pressure difference is 0. Yes, so we'll be getting this. This is the Newton's law of viscosity, tau r z equals to minus mu dv over dz. Again, substitute this law here. We'll be getting this. So again, integrate it as you can see there are two differentials. So for after first integration, we'll be get one constant c1. Re Rearrange it for second integration. Divide this mu r both side. We'll be getting a differential dvz by dr. From this dvz by dr. Again, if we integrate, it's very simple integration. This will be ln. This will be r square by 2. We'll get this. This is our final velocity profile. Now again very same. Now again we'll be having two boundary conditions. Substitute both, but in this case, what we'll be doing is as it's outside the film, we will be taking r plus delta. The delta will be the shell thickness. Okay, so the delta will be the shell thickness here. So again, the velocity at the r and r plus delta both will be 0 as previous. It's only the boundary condition only, nothing else. So both will be 0. So 0 equals to rho g by 2 mu. We just substituted that in that equation, in that what tau rz thing. So we just did tau rz equals to 0. You can see here. You can see here minus mu dvr by dr, and yes, dvz by dr is equals to 0. So we'll be getting this only. So substitute, we will be getting C1. Actually, we can use two boundary condition as radius, as velocity, or one flux, one velocity. So we are going with flux condition. We are going with flux condition. So this is our flux condition at r plus del. That means at the end of the shell. This will be the, as it's very simple, like the water is going downward. So at r plus delta means at the end layer of the liquid, it won't be going out. So dvz by dr will be 0. Substitute this, we'll be getting c1. Put c1, and using no slip boundary condition at r, we'll be getting vz. So this is our, we'll be substitute vz in 0 is equals to this, all this thing. C1 we have, so we'll be getting c2. We got c1 and c2, so we will be getting our final expression for, it's not correct written that much good, but it's correct only. So we'll be getting our velocity profile where a will be equals to r plus delta. That means the shell thickness. So we obtained our velocity profile. And for mass flow rate, again, mass flow rate, we have vz, then velocity into that 2 pi here it's nothing but just area into density into velocity. So as we can see from unit balance, it will be zero. It will be mass only, like kg, like kg per meter cube will be rho, and this will be meter cube per second. So kg per second will be obtaining, and this is how we'll be getting mass flow rate. So integrate it Vz from r dr from r to a. A is our r plus delta. That means throughout the shell, throughout the liquid film, will be integrating Vz r dr. So we'll obtain our mass by rule. After integrating, we'll be getting this. So this is our substitute velocity. Solve further, and we'll be getting mass like this. We have done nothing, just a simple integration using unit balance. We can see. So it's pretty simple. So just we will once we got the velocity profile, to get the mass, just multiply it by area and 2 pi rho. Like area into density into velocity, we'll be getting mass flow rate only, kg per second. So this is our mass flow rate. After rearranging, this will be looking like this. And here A is our R plus del. The R plus del, where del is our thickness of the film. So for now, the third part of the question, second part done, mass flow rate. First part was the velocity profile. Final part is A equals to R plus del. Now for del is very very small. That means it is very very thin film. So for that, after doing taking assumptions, ln a by r is equals to 1 plus del by r. So this I guess this is the property ln in bracket 1 plus x, where x is tending to 0. We take x directly because ln1 is 0 obviously. So ln in bracket 1 plus x, if x tending to 0, it's the same only. ln in bracket 1 plus del by r. A is equals to r by del, so r by r 1 plus del by r, where here r is very very greater. So we'll be taking del by r directly. So put there del by r in the ln by r in this place, and again club everything. This you can club, this you can club, so everything club. After clubbing you will be getting this. So this is our mass flow rate for very thin. This is for very thin. This is for very thin. Okay, so second problem is done. Now let's move further. And now for moving velocity profile and mass flow rate for two rotating coaxial cylinders. This is a bit different problem, but I have taken this because it's still relevant. It has the same concept as the annular cylindrical, because coaxial cylinder means that they are they have the same center and the same structure as of earlier. So yes, so we are with VZ with the difference here is earlier we were having that here fluid is placed stationary in the cylinder. Okay, it's placed stationary in the cylinder. It's just that that cylinder is moving. So just imagine the same annular region concept only, nothing else, just the same annular region concept only. Just the velocity will be in theta direction, not in z direction. VR Vz will be zero, and we will be adding velocity into in theta direction only. Now, as velocity in r and z is zero, there won't be any momentum. Momentum will be in only theta direction. So for this coordinate system, we will be directly using Navier-Stokes equation. Now, now the derivation of Navier-Stokes equation is already done in the assignment as uh, uh, earlier. So it's only the shell balance types. But for momentum transfer, we name it as a Navier-Stokes equation, nothing else. So after dividing by mu, we get this equation. Ah, so here, as it's a second order differential equation, to solve this, we know a method in that we assume v theta is equals to r to the power n, and as it will be r to the power n, its first differentiation will be n r to the power n minus 1, and n into n minus 1 r to the power n minus 2 will be the final differential of this. So it's written here only. This is the equation. So we will get 2n plus 1 and minus 1. Now after putting a r to the power plus 1 is equal to ar and b by r. So this will be our final expression for velocity. It is the solution of this is the solution of this equation only. This v theta is equals to ar plus b by r is the solution of that equation. Now we have two boundary condition. At r equals to r1, v theta will be w1 r1, and r equals to r2, w to r2, as both are different radius and both will be having the different angular velocity. Substitute it, we will be getting a and b. So we get this a. Just use those boundary condition. We have already done this in first problem. Substitution of boundary condition and simplifying. We did nothing. Multiply it by r1, multiply this by r2. We'll get this equation. Yes. So divide this term and we'll be getting a. We got a. Put a in any of the equation, we'll get B. We'll get B. Put A and B both, we'll get velocity profile. That's it. That was our objective, to find velocity profile. So yes, this is our velocity profile. Now the conclusion we can draw here is the tangential velocity is combination of r and 1 by r, as we found that kr plus b by r, and shear stress decreases with with radius is 1 by r square. Now as we got the v theta, we got velocity. Put tau r is equals to this from Navier-Stokes equation. Go in opposite direction. Now we have v theta, we need to find tau rz. So divide this v theta, we'll get this v theta by r will be this. Subtract it, a will get cancelled. We'll left with only 2b by r square, like 2b by r square and the mu. So mu from that side. So we'll get tau rz, which is inversely proportional to r square. So that is the shear stress decreases with radius as 1 by r square. So we derived both of the equation. So now let's move further. I have taken a concept here just for understanding about cylindrical coordinates. The reason to take this was it's pretty basic continuity equation derivation. As I already done a derivation earlier, this derivation is also helpful to understand the concept about cylindrical coordinates more. So it's just equation of continuity means mass flow derivation. So here we take r dr dt the dz. It's our elementary volume. In this, dr is one thickness, r d theta is another one, and dz is third one. So this is our shell. This is our cylinder. This is our shell here with three thickness. And multiply all this, we'll get volume. So this is our volume. This is our elementary volume. We got our elementary volume. So we are going to derive the equation of continuity. We got dv. Again, accumulation is equals to in minus out for uh, for this problem. So yes, the volume into rate of density. Now the accumulation rate will be this d rho v by dt. D because d rho v will become mass only, so mass per unit time will be our rate. So rate of accumulation will be d rho v by dt. Now let's go ahead and look at the entrance and look at the in and outflow. So the mass flow entering at r will be rho vr. Rho vr is our what? Rho vr is our velocity, right? So rho vr will be the flow entering at r, and r d theta dz will be the perpendicular area, right? Like the velocity, you can assume a velocity component entering in that area, so it's just perpendicular area. So this will be our mass flow rate, rho kg per meter cube, vr meter per second, and area meter square per second. Cancel out everything, we'll get kg per second, so it will be mass flow rate only. Just take it as like flux thing, like perpendicularly that velocity component is going under the perpendicular area. So this is for VR, this is for VR for R plus delta R. And now we got these 2 points for R plus delta R and R. For R plus delta R, the dr is very small, so we can break it. For at R plus at dr, it will be very small, so we can take partial derivative that like that limit term dr tending to 0. So we got this Taylor expansion. Using this Taylor expansion, we can add this. Now this is our net radial. Now subtract this that we will get net radial outflow. This minus this, entering out minus enter, rho VR will get cancelled. Left it only this term. That's it. And these are the, this were already there. RD, RD, theta, these are. That's, we have done nothing. Just in out minus in. Out minus in means this minus this. Rho VR got cancelled. This term is here, and R and dr will be there, and d theta dz. That's it. This is our net radial outflow. We got accumulation. We got outflow. So now this will be angular outflow. That was radial. This is angular. That's why we have taken rho v theta. That in angular direction. Again, for this thing, we have taken its perpendicular area. Look at this. This is the perpendicular area. In every case, just take perpendicular of any velocity component you are going with. So this is our net axial in vz direction. Again the same. Again perpendicular area. Dr d theta is there. So this is our net. We got axial. We got angular. We got radial. We got all the three inflow and outflow, and we got the accumulation term as d rho v dm by dt. So equate everything, net outflow will be like this is axial, this is angular, and this is in z direction. Sorry, this is axial, this is radial, and this is angular. So on simplifying, we'll be getting this. Actually here is equal to psi, and here actually that accumulation term is there, so leave it. So here this will be a final equation. This outflow is equals to accumulation. That accumulation will be in this side, so just rearrange it. After rearranging, we will be getting d rho by dt plus 1 by r dA by dr, r rho vr plus 1 by r, 1 by r d rho v theta by d theta plus d rho vz by dz equals to 0. This is our final equation of continuity. What we done? We got all the net outflow, we got accumulation term, equate both sides, equate everything, then take it on one side, rearrange it, and divide everything and make d rho by dt separate. So this is our final expression of equation of continuity. If density is constant, then d rho by dt will be 0, will be remaining. And as we can see, density we will take constant, as we can take out and divide the whole term by density. So we'll be getting this as, for constant density, this will be our final continuity equation for cylindrical coordinate system. So yes, this was the nothing but mass balance for a differential cylindrical element and continuation of it for incompressible flow as d rho by dt is 0. So yes, overall conclusion is we studied flow through annulus, we studied outside the circular tube, we have studied about rotating, and we have studied about the equation of continuity. So this was the whole about cylindrical annulus, not just annulus, it was more about cylindrical coordinates. So we started with annulus and go on with the difficulty of the problem. So thank you everyone for listening this lecture. I hope it helped you, and thank you.